Hello everyone, welcome to our presentation about Interspeech 2020 paper, Adventitious Respiratory Classification using Attentive Residual Neural Networks. This is the information of all authors. My name is Zhang Yang, I'm from Chair of Embedded Intelligence for Healthcare and Wellbeing, University of Augsburg, Germany. And our professor is Professor Björn Schuler from Imperial College London and the University of Augsburg. In this presentation, I will give you an introduction about our proposed paper in several parts. Recently, COVID-19 affects the whole world, and there are more than 33 million confirmed cases and more than 1 million deaths caused by COVID-19. As a respiratory disease, COVID-19 has some classic symptoms, for example, adventitious breathing, fever, and coughing. But for patients, fever and coughing is easy for them to recognize, but adventitious breathing needs some professional medical or doctors to recognize. So adventitious respiratory recognition is more urgently required nowadays to help the doctor to diagnose COVID-19 and other respiratory diseases. So the main contributions of our work is a ResNet-based neural network model along with 4 different attention mechanisms. And also our approach overtakes currently available methods on ICBHI 2017 database. First, I'll introduce the residual network. The left figure is the architecture of 2 layers convolutional module, which includes 2 convolutional layers with ReLU activation functions. The right figure is the architecture of 2 layers residual module. It is based on the convolutional module, but before the input is fed into the convolutional layer, it is saved and marked as the identity, and at the end of the residual module, the original output and the identity will sum up, and the sum of them will be regarded as the output. This is the architecture of ResNet 18. The first layer of ResNet 18 is a convolutional layer with 7x7 filter and 64 channels. The second layer of ResNet 18 is a max pooling layer. Then followed 4 residual blocks with the number of the channel in 64, 128, 256, and 512. At the end of the ResNet 18 is average pooling layer and a fully connected layer. We tried some deeper architecture of ResNet, for example, ResNet 34, 50, 101, and 152, but they caused severe overfitting. So finally we decided to use ResNet 18 as our baseline. Then I will explain all 4 attention mechanisms applied in our paper. The first one is squeeze and excitation. The size of the input is h times w times c, means the height, width, and the channels. First, we use an average pooling layer to get the channel descriptor from the input vector. Then we used 2 dense layers to change the length of the channel descriptor from C to C of R, back to C again. The output of the squeeze and excitation is calculated by using the input vector multiplies the channel descriptor. And the equation of the squeeze and excitation is here. The second attention mechanisms we applied in our paper is spatial attention. So we use the convolutional layer to extract the spatial descriptor from the input vector. Then the output of the spatial attention is calculated by the input vector times the spatial descriptor together. And the conv 1 times 1 times 1 means the size of the filter is 1 times 1, and the output channel is 1. The third one is squeeze and excitation plus spatial attention. So it means we extracted the spatial descriptor and the channel descriptor at the same time, and the output of the attention is calculated by multiplies the input vector, the channel descriptor, and the spatial descriptor together. The last attention mechanism is component attention. So we use a convolutional layer to extract the component descriptor from the input vector, and we multiply these two things together to get the output of the component attention. So for the convolutional layers, its filter has a size of 1 times 1, and the number of the output channels is C. The database we used is called International Conference on Biomedical Health Informatics, also known as ICBHI 2017 database. This is the Attentive Respiratory Cycles database, and it contains 128 participants and 920 recordings together. And every recording was divided by every respiratory cycles. And there are 4 classes in this database: normal, crackle, wheeze, and both, which means crackle and wheeze at the same time. So in total, there are 6,898 respiratory cycles in total, and for training sets there are 4,142 cycles. For test set, it has 2,756 cycles. So for our experiment, we did a subject-independent partitioning on the original training set. We followed the same preprocessing procedures as state-of-the-art work, and including downsampling all audio files from 44.1 kHz to 4 kHz, and applied the 5th Butterworth bandpass filter to keep the information between 100 and 2000 Hertz. Besides, we trimmed all audio files longer than 2.5 seconds to 2.5 seconds, and padded all audio files shorter than 2.5 seconds to 2.5 seconds. The feature we used is spectrogram, and the parameter of the spectrogram extraction is the number of FFT is set to 100, and the window length is 100 milliseconds, and the hop length is 40 milliseconds. We used the same evaluation metrics as the official ICBHI 2017 challenge, and to make a clear comparison between our proposed works and the state-of-the-art works. The evaluation metrics include sensitivity, specificity, and the average score. In the equation of the sensitivity, CT, WT, BT means the number of the correctly classified crackle samples, V samples, and Bose samples. And CWB means the total number of the crackle, V's, and Bose samples. And in specificity, NT and N means the correctly classified normal samples and the total number of the normal samples. The average score is the mean of the sensitivity and specificity. This is the results of the state-of-art works and our proposed works. And in this table, the upper 4 rows is the result of the state-of-the-art works. Their result on validation set is not available, but in the test set, the best result is 50.16% of average score, which is performed by the STFT plus wavelet features plus by ResNet 34 model. And for the lower 5 row is our proposed work result. And for our baseline, which is the ResNet 18 without any attention mechanism, achieved 51.19% of average score on validation set. And on the test set, it achieved 48.71% of average score. The best model on the validation set is the ResNet 18 plus special attention, which is 54.49% of average score. And on the test set, the best model in our proposed work is ResNet 18 plus squeeze and excitation plus special attention together. This model reached 49.55% of the average score, which is equivalent to the best result in the state-of-the-art work. So in conclusion, our works proved that attention mechanism improves the performance of residual neural network on attentive respiratory classification task. On the validation set, the result improved from 51.19% to 54.14%. And on the test set, the result is from 48.71% to 49.55% of average score. And our best model on the test set is ResNet 18 with the squeeze and excitation and special attention together. This model is equivalent to other state-of-the-art works, but with a much lighter model, which can alleviate the request on computational complexity. So the best model of the state-of-the-art works used by ResNet 34, which means 2 parallel ResNet 34, and it is more complicated than our model. So our model can save more time and storage resources. Our future work includes applying other feature set because the state-of-the-art works uses several different kinds of feature sets, and also data augmentation should be tested to deal with the unbalanced database. And these are the references we used in this presentation and the slides. And thank you for your time and patience for our presentation. And I hope you have a nice day and enjoy Interspeech 2020. Thank you.